What a great song to come on.
labs for this week. So that the bathymetry lab, which should be pretty fun today, and then lab 4 sediments. That should also be kind of a fun one. So you can pick those up now or later. And so I still need to fix the syllabus, admittedly. But our plan for today is to hopefully get through chapter 2 and 3, so we'll see how that goes. So 2 and 3 today, maybe 4 and 5 on Thursday. Again, we'll kind of see how today goes. Worst case, next week, if you're kind of looking ahead of the schedule, we also have next week slated for chapter 5. So if we have to push chapter 5 all to next week, that's okay. And then we have our midterm that Thursday. So just keep an eye out for that. Oh. All right, so today we're starting our plate tectonic theory. And the book, or not the book, the video that we watched was really nice in explaining all that. And so we'll kind of go through again what we saw in the video, kind of the history that supported that, and of course how we kind of model that, and how things have changed over time. And so like the video had mentioned, Alfred Wegener first came up with some idea of continental drift in 1912, and he even proposed that at one point there existed Pangea and that the continents kind of fit together. And so again, this was towards in the 1960s. And so what was the problem with his theory, and why did people kind of mock him, and or what did he have wrong? What did he have right? Yeah.
He had it right that they were moving, he just had it wrong how they were moving.
Do you remember what he thought caused the movement?
They were being pushed.
Yeah, but do you remember like what he gave like a few things that he thought it was, like do you remember? Does someone else remember or want to tack on to that? Aliens are always the answer.
Like they were driving across instead of the liquid underneath.
Yeah. So exactly. So we had no understanding of at least plate tectonics. So we still aren't sure of the mechanism. We'll kind of get into that, but at least we kind of think that's what's driving it. And so he thought that it might be from the tides. So here's what he got wrong. So it was from tides or some sort of ocean movement. Or, you know, he didn't quite know, like you were kind of saying, just that he thought that they were moving, but the forces that he was kind of proposing, that just the ocean movement was enough, or some sort of gravitational force, that wasn't enough. So some people, of course, mocked him, the idea that the continents were moving. And this is, I mean, it's kind of crazy. You have to appreciate how much we've proposed in just the last 100 years. And so it wasn't until the 1960s, like we were watching in the video, that we started using more computer models and fitting into. So what was the key and how he fit that? So there's kind of, you can kind of see it in the outlines here. But what was his estimate? What did his estimate do? Yeah, there was something about his computer models that made it fit better. Yeah.
Because instead of going to the edges of the land, they went to the edges of the continent.
Well, exactly. So he didn't know that he was going to the edges of the continental plates, but instead he made this rough estimate, and he made it. I was trying to find the exact number back in the book now. I think it was about 1,000 kilometers plus out in some areas. So just like she was saying, what that ended up doing is instead of just modeling the continental crust, and what also they didn't understand initially when they were proposing this, is that you have both our continental crust and our oceanic crust. And it's really those oceanic crust movements that are kind of driving everything, and those oceanic plates are further out, and so this model was more accurate, and since it turned out to be modeling kind of the oceanic plates. So it ended up modeling. And so again, this seems pretty amazing that this was fairly recently in the 1960s. So we're kind of seeing how they came together potentially. And so other evidence was, of course, matching sequences of rocks. So we mentioned here the Appalachian Mountains have similar features to mountains in Europe, which is kind of strange, since obviously they're very far apart now. And so a lot of the evidence was also really strong in South America. So that was also really interesting at the time, since when they were kind of debating it, a lot of these South American and African scientists who were studying it here were saying, yeah, they have to be together because they found really strong evidence. So do you remember, what did the video kind of mention too? What do you remember from the video? What did they find?
The similar species.
So similar species of animals. So identical fossils. The same species.
I don't know if I read somewhere else, but didn't they find similar and identical, like trees and growths?
That could have, yeah. Yeah, that would, so trees, same thing. Let's put under there rocks, of course. Excellent. Anything else you want to add into there? So yes, this was a big clue, and all the scientists who were studying this on the ground were really saying, yeah, this had to be the case. And kind of the North American scientists were a little bit more behind because they weren't seeing just as strong evidence at the time. Of course, you know, the Appalachian Mountains map matched up, but at the time they were really studying this. This seemed kind of very obvious, so that kind of led to them studying other things. So they kind of had to catch up with the information there. And of course, other evidence and for how the continents might have moved is, of course, we can, you know, go back and surmise that some areas were experienced an ice age, except now they're at the equator, so how could that have happened? And so perhaps they were at one point, though, more towards the poles, and therefore would have experienced an ice age. And of course, we have fluctuating climates, so all that plays a part. And of course, right, this is our best guess of what's happening. Everything's always changing, what we can gather, evidence, you know, and we at least can tell like the sequence of how things happen. You can tell how the rocks layer, but you know, it's all a lot of modeling, what we think happened, and there's so many factors, right? What the climate was, where the location was. So it's a lot of area of research though. So excellent. So we went over that. And so there it was, 1915. He published a book about it, but again, what he proposed, so he had the wrong mechanism for action. So the tidal gravitational attractions were too small, or any sort of oceanic movement, none of that, all of that too small to move continents. So some other ways that we can tell what's been going on in the Earth, and also how things have changed and how the continents have drifted, is through the magnetic field. So first we have to understand that the Earth is a magnetic field. And so everyone's familiar with a magnet, right? And so you know that it has some sort of poles, right? So it's got polarity. And so this is because you have to have some sort of material that is going to be magnetic. And so that can be iron. And that essentially just means that the electrons are susceptible to aligning. That's how you get the polarity. And so especially in our mantle core, so of course we have a bunch of iron in there and it's circulating about. And, you know, again, we're not entirely sure how to get this magnetic field perfectly modeled, but it roughly models as a magnet. Yeah. So it's mainly going to be the inner core, because remember, right, so then the iron has a line. So at one point, right, it's molten, the iron lines up, and so you have your solid iron core. And again, right, we're not entirely sure of the mechanism, but iron, we do know, is a ferromagnetic material, so it's susceptible to being magnetic. And then if you align it, right, it's just like a magnet, so you get your magnetic field. And what's cool about this is, of course, then you can see the magnetic record. And so again, the Earth has magnetic polarity, so just like a magnet, we can assign one as north and south. But what's also fascinating is we can watch how the Earth has actually shifted in magnetism, so the polarity, and that we are not sure of the mechanism. That is interesting. And so of course you can look at the magnetic field. So if you have one of those, a compass, right, a magnetic stick, so it tells you which direction is the North Pole. So if you stand at magnetic north, it points down, so straight down into the Earth. And again, that's going to be the magnetic North Pole. So it's not the same as we've defined as our geographic North Pole. And of course, as you may have read, that magnetic North Pole has wandered and continues to wander to this day. And then, so if you were to go down to the equator, so here's our bar pointing down, just so you can see. So now at the equator, it stands parallel at the Earth. I didn't draw this very well at all, I'm sorry. So it's pointing down. Now at the equator, right, notice how it's parallel. And then if we go back to the magnetic south, so then it would point down, except now the opposite of this end, so kind of pointing outward at the magnetic south pole. And so we can study this, so the field is called paleomagnetism, and so that's just the study of Earth's ancient magnetic field. And so what we find is, so any place you have seafloor spreading or right, the mantle coming up and making new Earth, so all that is going to be igneous rocks, which are basalt, and all these are high in iron, and so those are able to, of course, in their molten state, they're free, they're moving, so they're going to line up with the magnetic field. Then they cool, solidify, and then they're frozen in there for the rock record. And let's see. Just looking. Oh, I put a picture in there. That's cool. And so you can look with the rock record then and see the bands and see where it flips. And so they roughly find that about every 5,000 years the poles flip. And of course everyone's kind of saying we're overdue for a flip. So maybe our poles will shift, and we'll see what effect that has. So of course animals have some sort of electromagnetic sense that they use for navigation. Yeah.
Now, over the last, several thousands of years, we haven't had as many electronics and things like that. What would a reversal of that cause, could that have like detrimental to like electronics and power plants and stuff like that?
I'm not really sure. I don't think it would have like too much of effect other than, we don't know what like a pole reversal would look like. So if it's like reversing, like what if the magnetic field temporarily drops, and then could that cause like solar flares? And so like solar flares and spikes, that can have an effect on electronics. And then, how strong is that gonna be? So there's so many variables. But again, we don't even know the mechanism of it. So the book mentioned that they tried modeling it, like how it went, like maybe it had something to do with the currents, but in their modeling it flipped too much. So, if we're not sure of the mechanism, then we can't even say, is it gonna turn off? Is it just gonna be a weird like flipping, and then it would just be anything that's magnetic would just be flipped polarity wise. So then your compass would point the opposite way temporarily, right? Or, well, not temporarily, like permanently. So then whatever used to be north, like the red points north, now the red's pointing south.
Oh, interesting.
Yeah, so that would be like the biggest effect, and same thing, so then animals would be all turned around, so that they'd be thinking they're flying north, but then they're flying south. But, yeah.
Actually hard on the species,
Yeah,
trying to go where it's warmer and they end up where it's cold.
yeah, at least, assuming that, like, who knows, what if they somehow, like, readjust it? I have no idea. Like, that's only us guessing, but that's our best guess, is, because we're not entirely sure how the animals even sense the magnetic field, since, humans can't sense it. So we can't really understand how the animals process, but yeah, that's our best guess, is it would be confused. If it were to happen, we would get to study that and see, like, who is affected, do they do weird stuff. And so, of course, what's fascinating is even, right, in the past 200 years or so, it's moved a lot, our magnetic pole, so it's just been kind of wandering this way. So again, there's still a question, will it just keep kind of wandering? Will there be a flip? Because it looks like there's a flip, but again, in our rock record, but we're just not sure what that's going to look like on our kind of day-to-day, year-to-year time scale.
Do they say about how long it takes for it to reverse?
So they say it flips so every 5,000 years. So.
So is it like you're progressively shifting in that 5,000 years, or is it happening within like a week of that 5,000 years?
No, it's like a huge range. So I think right now it's been 7,000-ish years, they estimate, since the last flip. And I'm trying to reference.
Okay.
But yeah, I mean, so they think, because, again, we don't really know, because your book mentions that it kind of ranges from 25,000 years to 30 million years before switch. So it's not like a regular pattern, which is, of course, difficult to model too then, because, then we don't understand if they're like variable forces, how can we model that? So.
Because I'm sure that, depending on how long it takes, would affect, the animals and the other species.
Yeah, but it's all going to be on like.
If it's a gradual thing, as, animals move on and they do their thing, they're just gonna kind of adjust as it changes with it, I assume.
Right.
Versus if it just did that and now it's
Well,
reversed.
Well, that's just, I mean, we're assuming that it's going to be a fast reversal, but it switches right every 5,000 years. But I'm just saying, like, we can't tell from the fossil record, right? Is that a quick switch in a day? Is that a year? So that's kind of more ambiguous what's going to happen. But we can tell from the rock record that it does switch, but then that's not regular, right? So we don't know what mechanism is driving it. And so that's kind of variable. And, that's why we say we're overdue. But if we don't know the mechanism, we can't predict it.
Okay.
And that's just an average, that's not a.
Right.
That's not a solid answer.
Yeah, and it could be another 30 million years before we switch. Like, who knows? We don't know. Or it could switch tomorrow, and then we'll all find out what actually happened. Like, I'm open to it. And so back to our continental drifts. and how we figured out how they might have drifted and what pattern is, so for a second there was a discrepancy of where the North Pole is. So we agreed on the present day location, but based off of how things look in their present locations, you could draw it like that, and well, that doesn't make sense, because was the North Pole here or here then, right? And so in this case, they found that they could actually reconcile the data by moving the continents together, and so now that kind of maps a lot better, and so it looks like, right, that's consistent with where a magnetic pole is, but then that also tells us that, yes, the continents did shift over time. And so again, let's just go over some terms. So magnetic anomalies, so that's just the regular pattern of north-south magnetism stripes. So again, you would see that like on the seafloor, and they can use, right, your magnetometer, and that's what measures what orientation it is. Well, it can tell the flip, because because basically, and let's just pretend, right,
You're saying the regular pattern is a little misleading because the pattern is alternating.
yeah, well, it just means regular as in regular alternating, because then, yeah, and the other kind of strip, so remember what was fascinating, okay, so this, let me start over. I'm trying to draw a graphic, and that's not clear enough. So what they're saying by regular, so let's just say in the center, it's all going up, right? And then by regular, what was kind of interesting, what they noticed, so then this would be down, 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 is it was kind of mirroring. So they could also tell that there's some sort of like seafloor spreading. So that's also the information that they got from that. And so what that tells you is that at one point, that probably these came out of the earth together because they're regular intervals apart and they're the same pattern, right? And then this one came out of the earth, newer, so then they're closer to the source. And then this one, right, hasn't split yet, so that just came fresh out right at the source, coming out in that direction. So that's also regular. So yeah, just that alternating stripe pattern, and then again, it's coming out from the center, so that's telling us where it's originating from, and we can, tell that it's splitting, like we're going to learn, or you saw in the video. And so again, they're symmetrical stripes, and they use that magnometer. So it's just an instrument that they tow behind the ocean vessel, and they, have to go around the seafloor, and then watching that magnetometer switch directions, so you tell which way it's aligned. And again, that's how they got that pattern. All right, so now, how do we map the seafloor? And so we had this guy, and again, relatively recently, right, that we're mapping the seafloor, which is also kind of weird to think about, since you can look around and draw the mountains easily on the land, but the seafloor, right, we can't see. And so Harry Hess was a submarine captain and geologist, and so he, I think, just had a depth recorder on his submarine, so he just let it go all the time. And so his depth recording at least started to show that the ocean was irregular, so people didn't even know, like, is it one big flat thing, or, and what he found that really it's as diverse as the terrain we see on land. And so now we're getting into the seafloor spreading. And so, y'all were kind of mentioning it to me earlier. What happened to my pen? The mechanism, so of course, the mechanism, does anyone want to explain it again? Kind of what we at least, the simple mechanism,
that causes,
the continental plates to move, so yeah, either go crash or spread,
Yeah.
so what drives that? What drives the movement? We said it earlier, but then what drives the tectonic plates, so we think?
Wasn't it heat?
Yeah, so heat, right? And what was the key term? It's on the graph. You can read it. Convection, right? So that kind of circular movement that kind of keeps it going. And again, we're not entirely sure, but it seems to make sense. Kind of like, a lava lamp has the same sort of mechanism. You have your heat source. So of course, right, it's hotter as we go down. So the hottest thing is here, but then hot stuff rises, right? It's less dense, so it rises to the surface. And then eventually, right, in the seafloor spreading we see here. So eventually, right, they started mapping out the ocean. And so between North America and Europe, they started figuring out there's some mid-ocean ridge here. And so looking at this, we find that it's a spreading center. And so at this spreading center, again, being driven somehow by convection roughly, now we have our hot molten rock coming to the surface, and of course comes up, cools, and like we mentioned with the magnetic pattern, cools in that pattern. And so we can have also subduction zones, so that's going to be the oceanic trench site of a crust subduction. So here we have subduction zone, so oceanic crust going in, and that can even fuel volcanoes potentially. So does anyone remember a volcano kind of near to us that might be fueled by this? What'd you say? Yeah, Mount St. Helens. So this is not right on the plate, but pretty close. And so the idea is this new material that just came in. So now it comes in, it gets melted, and it gets all hot, and then it comes up, of course, and comes out as a volcano. And so your book mentions too that, right, how explosive the volcano is kind of depends on exactly the material composition of whatever this rock has to be. And so, depending on what it is, it might be more explosive and more ashy. So that kind of gives it the different characteristics. And so you can also have, of course, subduction zones that just create deep trenches too that we see in the ocean, like the Mariana Trench. Oh, sorry, repeat of that. And so this is just, again, another look and visual of how the seafloor is splitting and how we can see the magnetic field. So again, lava erupts, it aligns itself since it's very iron rich. And then we can see how that pattern is repeated and spreads out. Then you notice the reversal. And again, you see those normal rocks moving away in both directions. And so what does this tell us? Let's look at this and try to surmise what this might tell us. And so what's the issue here? So they've done some deep sea drilling trying to date the rocks. And so what's the problem that we see with this? or like the age of the Earth, right? So we'll say younger, at least than we think. And so what's kind of fascinating, though, about this? So what do we kind of see in this? What data could they surmise then? And let me show the key. What could we even say? Let's just look at North America and Europe, too. Kind of what can you tell from that? Looking at the age.
The red is the new rock, the mid-oceanic ridges. And as you go further from that point, it gets older.
Exactly.
Except for to the right of where South America is, it got swallowed up.
Oh, yeah, like kind of here-ish, you're saying?
No, up
That's
to the west of South America.
west, sorry,
It's all
south.
new.
Oh, it's all new. Sorry, I see what you mean. And so that's interesting, right? So what is this? So this is telling us a lot of things. So you were mentioning, right, you have new material everywhere. So new. So we can see this is in the middle. So that's telling us, right, where that mid-Atlantic ridge is. But that's telling us, right, where the seafloor is splitting. You can tell, right, what direction then they're moving. And, we'll learn they also kind of guesstimate how fast, because you can see, right, how much area too. So you can try to guess. And then those were interesting observations, right? So you're right, what happened to the old rock here? And so maybe we'd have to look at our tectonic plate map and see what was there. But if the oceanic crust is just going in and being consumed, then that's where our old material is going, right? So this is also telling us that the oceanic crust is always getting renewed, always going back into the mantle, getting boiled down, coming back up.
Could it just be getting pushed out?
It's hard to tell. I would have to look at the map again because I'm trying to find the other map that shows the direction of all the tectonic plates. Yeah, this is what we want to look at. So then the question, see, I think kind of looking at that, because look, this is a convergent boundary here. And so what you may have there, so that's going to be then where the oceanic crust is probably diving in since it's convergent. Or it's showing mountains, we have to look at that area. Or it might just be creating then landmass, right? They're going up and creating the mountain range, which that kind of looks like what might be happening.
All of the convergent boundaries have mountains and that's what that represents.
Yeah, and that is, they do create mountains. I just wanted to look at what crusts there were too. But yeah, if there are mountains, yeah, because you also have mountains here on the ocean floor too. So that's probably what's happening. And there could also be some material, right, being subducted too, and then rising back up to form the mountain that, if you remember from chapter 1. It's just that you have to look at the specific boundary too, specifically to see what's going on. Yeah.
Is there a chance of a lot of the old rock just kind of got covered up, like they say when it's the supercontinent? It was like when you make little sand castles on the beach, like volcano rock pile here, and then it kind of fills in, and then they sort of float around. Like a lot of them have older rock borders that like lava was kind of flowing outwards, it would cover them, and if it sort of floated on top because of the lighter granite. Like deep below the land masses, there won't be much older rock.
I totally see where you're going. I'm not sure there's like evidence for that because we have to think about, because we have, right, our oceanic crust. So it's also, it already sits lower than your continental, right? Because you have your continental crust that's more the land mass, and then the oceanic crust underneath that our continental sits on top of, right?
Yeah, we're saying all the oceans are a lot younger when they go under the land masses, they're a little older, and they said that they formed by floating on top. It's just a maybe. That's all.
Yeah, well, I'm just trying to walk you through your thought though and say
Yeah.
like, here's what I think like the holes are, because you have to think of where the oceanic crust sits and where they got the samples. Like, I get what you're saying, but that means that might be more like this area where the rock is probably being transformed into
No,
a mountain.
That's what I meant.
So it's
like
kind
dark
of-
brown borders against the edges of the landmass.
Yeah,
And all the younger rocks spreading from the center. Something still go undersip up to. It's just.
yeah. But like so then the broad idea, right, that we want to summarize though, is that our oceanic crust is always on the move, basically, right? It's, and this is, again, relative to our continental Earth. So our oceanic crust is getting more recycled, it's moving, right? We can see which way it's moving to from the magma. And then right this, where it's all new and where we can see active spreading, and I think it was in a later chapter where it mentions where they try to see the volcanic eruptions like live on the seafloor. So that's all where we can see from evidence of it splitting. And then this also tells us, right, that this is where kind of the action is happening while these continental crusts aren't really getting recycled like the oceanic crusts are. So that's the other difference, is the continental crusts kind of sit on top of the oceanic crust. The oceanic crusts, right, supply a lot of the material, and while most of our continental crust just kind of stays there and floats around. And I always like this picture. This is just a really fascinating picture. And so, of course, this is just mapping the activity of earthquakes. And so what do you notice about the pattern of earthquakes and kind of what helped give kind of credit to our continental plate theory as well? So they're all along the line. So they fall along with our continental plates, the highest concentration of earthquakes. You see that all along these lines everywhere. What's that special zone called with like the most earthquakes and tectonic activity and volcanic? Yeah, Ring of Fire. So all that from our tectonic activity. And so this is a nice graph too. And I think you had to do this in your lab, right? So just kind of draw it the best you can. I know Australia was in a difficulty. And so again, we can at least guesstimate what general direction they've been flowing, whether we're getting farther apart or closer together. And of course, that goes back to, eventually this distance is going to get further and further apart between North America and Europe as those plates kind of spread out. And we have the San Andreas Fault, that's pretty famous. All right, so let's look at our three main plate boundaries. So I want to know these. So our main one is divergent. Oops, oh my gosh, sorry. So divergent, of course, meaning they're moving apart. And like we've mentioned, this example, of course, that we've been studying is the mid-ocean ridge a lot. So moving apart. Then we can have our convergent plates. And so this could be a deep sea trench, or if this was two continental convergent plates, it may make a mountain ridge instead. You can still have, right, landmass go up though, too. So it kind of depends whether it makes a trench together or goes up. And then we have our transform, like that San Andreas Fault, where they're just kind of sliding past one another. And so looking at the different types then, so this is a good chart as a kind of cheat sheet, what's what. Because what you have to look at is what crust is coming together as well. So if it's divergent for oceanic, so just like again we've seen in the Mid-Atlantic Ridge, that's going to be seafloor spreading from that volcanic activity. And so just list again some examples. So when we see the divergent movement then in continental plates, then you could potentially, right, just get this continent splitting apart more and more, and so potentially create some new sea floor. And we see this, let me see, thought I included a picture. Yes. Oh, sorry, the caption is blurry. So this is in Ethiopia at the Afar Triangle, and so this is some divergent plate movement, and it just kind of split apart there. And you can see, I know the people are really fuzzy, but you can at least appreciate how tiny the people are versus how large that little split was. So kind of scary.
How long does something like that take?
This was just like one earthquake
Okay, that
incident.
was just an earthquake.
Yeah, so it split it right that much. And so you could see, because right, eventually what it could lead to, we go back to our cheat sheet, right, is new sea floors. You can imagine, right, that to take several big earthquakes over who knows what time scale to actually just really split it open. And that's what's slowly happening. If I go back to the specific picture here. So that continental boundary, they're divergent, and then these are continental plates, and so now they're starting to split. Yeah, and they're right there at the Red Sea, so eventually it could be oceanic plate form there. Because are you talking about the San Andreas Fault, or? Because that's a different kind of. About which one? Sorry. Oh, I could have misheard you too, though. Oh, I was just.
I read something where, Baja, California has split from Mexico.
Let's see. I'm trying to see. Yeah, I would have to look at exactly what you were referencing. Because at least, like, you can see, because California, like Mexico would be here.
Fault is from an earthquake.
Yeah, but this is the San Andreas Fault. So all I'm saying is it's a different kind than the divergent. So it's a different motion. That's all.
There is a portion though of the San Andreas Fault that is pulling away from the mass, like the land.
Yeah.
Yes. So there's, even though it's going this way, there's actually a part of it that's moving, I guess, west, and it will eventually be completely severed from. So it's like a peninsula right now. It's a very small portion, but it's, scientists have seen that it's pulling away from it.
Our friend Google, was just coming to the Baja California Peninsula, it's become part of the Pacific Plate, so it's now moving away from the eastern Pacific rise in the north-northwest direction along the coast of Santa Rosalia, Baja California.
But does it say if it's transform or divergent plate? That's.
No, just that it's joined, it's now part of the Pacific Plate.
Can you ask your search engine that? Because that's my point. That's my question. Because I'm just curious what.
Continental transform.
Yeah.
Yeah, California sheared up landscape, the movement of the Pacific Plate past the north edge of North America along the transform plate boundary.
Okay. So transform. So that was my point. Is yes, they are moving. Yes, they were split, but it's different from the divergent plate movement,
Yes,
right?
correct.
Okay, that's all I wanted to, that's all I was trying to say.
It's being pulled up and north, up along instead of just sort of like banana split.
Right. So that's, right, just different movements is all. So we have your divergent, where they're just moving more apart, versus transform, where they're sliding in different directions. But like, yes, they will be pulled apart.
Well, both of that's going on on the San Andreas, where you can see it. So you can see when you walk the fault line, you can
Yeah.
actually see that it's the divergent, where
It's transformed, transform.
sorry, that it's moved like this way
Yeah.
versus apart.
Exactly, yeah, so it moves,
And then part of Tamales Bay is actually moving out like Baja is.
yeah. So that would be, right, the transform plate boundaries. So San Andreas Fault, so you've been out there, you've seen it?
I grew up there.
Oh, yeah, that's awesome. Yeah, it's cool to go out there. Like, if you haven't taken a trip to see it, like, you gotta just look at how the earth moves. It's cool. And so we can also have that same sort of movement in the ocean, so oceanic crust. And so one of those examples would be the Mendocino Fault. And so this is where we were looking at, so we'd have to look at what is what for the crust. So if you have oceanic versus continental, and so this is where we remember, right, oceanic is dense. So if oceanic and a continental meet, oceanic's already going to be lower because it's denser. So then we get subduction, where one of them is going under, and of course that means our sea floor is destroyed, reproving our theory as to why the ocean floor is, again, so much younger than the continental crust. And so this could result in potentially a trench, and like y'all mentioned, that could give us volcanic arc then on land. So Andes Mountains and Peru-Chile Trench are some examples of those boundaries. And then if oceanic meet, so they're both, right, dense, you could still have some subduction, and again, not quite sure exactly what's going to happen, but some sort of trench as well, and potentially, right, volcanoes, like we'll look at, where you can create islands then randomly from a near a subduction zone in the middle of the ocean. You know, like that's kind of how the Hawaiian Islands formed as well. So that could potentially happen. And so like we see though, if we have continental crust meeting, so they're both lighter, right, they're both floating, so then they both just crash upward instead. And so that's how we get the really tall mountains, like of course the Himalayas, the Appalachians, so all those are continental. Blah. Kind of looking. So that's just divergent recap. And so of course, depending to how fast or slow it's spreading, you can analyze these rift valleys and of course get you see there's that African Rift Valley. And so again, what's also fascinating is in this region is just all the mountains, and so you can just see the different elevation. So brown and white is high elevation, and of course where it's splitting is a lot lower, so looking at like this lake. And so this is just different mappings too of the Mid-Atlantic Ridge. And so you can see the profile then of a kind of slow spreading ridge. And so you can see right the gentle slope there. And so fast spreading ridge is broad and even more gentle, so just almost kind of the same. see. So this is just kind of recapping the little chart. So again, convergent boundary. We see those coming together. So this is right, oceanic versus continental, just seeing that. And again, where we get that volcanic activity. So you can see that melting, and then of course that hot material will come up. And as our continental crust moves, then of course, right, we get the little islands formation, and the islands kind of move along. And that's how they predicted the age, too, of the Hawaiian Islands. And so up here we have oceanic continental convergence with these plates, with the ocean plate being subducted. And so the Juan de Fuca plate is again responsible for Mount St. Helens, so you all said that. So excellent. I would probably star that, remember that. And so do we feel comfortable on this? So continental, continental. And then let's just look at the pictures. So this is, again, fascinating. And like she was saying, you can see how they move past one another, how they're sliding the Pacific plate and the North American plate there. And of course, they can measure that rate there. And so then, right, they had the just mantle plume mechanism, again, just showing us how we made the volcanoes. Again, not entirely sure of this mechanism. We just have our general convection mechanism that we can presume. And then as new material goes in, then they suspect there's some sort of plume of hot buoyant material from whatever oceanic crust just came in. And then, of course, it continues to rise, and then eventually gives way to a volcanic hotspot. And this could be right even the ocean floor, too, where this volcano is, and then rising up. So we mentioned that as well. And that was, of course, right, the explanation for all these hotspots is it's somewhat related to the crust being subducted and then hotspot being created. So of course Yellowstone comes from that. So obviously we enjoy Yellowstone on a daily, yearly basis, but who knows if it'll still be there, you know, so many million years in the future. Or it might just shift around where Yellowstone is, like, so it might change, I'm not sure. Just like, right, again, the Hawaiian Islands obviously have tracked, they can track which island is oldest versus newest, so they could tell which direction it was moving. So eventually, all these hotspots might move too. So there are the Hawaiian Islands. So again, the relative ages shows you the direction. So Hawaii being the youngest, so the plate is moving that way, since Kauai is the oldest. Who's been to Hawaii? Nice. Oh, nice. See a lot of people. I should have brought back sand samples for us. I hear they have nice sand there. Really? What? Oh man, I've heard of that at other beaches, but I didn't know Hawaii was. I haven't heard of that for Hawaii. Not sure. All right, so I'm trying to finish up this chapter. So if you remember right from our volcanoes, eventually they can become seamounts. So seamounts are just tall volcanoes formed at volcanic centers, such as the Mid-Atlantic Ridge. And so these seamounts, they could potentially be peeking out as islands, or perhaps If they become islands, they could have their top eroded away and become a table mount. So be familiar with these terms. So the table mount, again, is just the flat top. Now that kind of makes sense. So at one point could have risen up was an island. If it got eroded away, chopped off, kind of like our table rock. And so, of course, we might see evidence that it could have been water at the top, so you can, again, see that. But what's also kind of fascinating is that these volcanoes could eventually make spaces for barrier reefs. And so looking at how this would have gone, so we had, right, a volcano, and of course materials being deposited here, so this would be called fringing coral reef. And you could have a coral reef here, which is just on the edge here. And then over time, and if the landmass kind of settles, and so notice, right, it kind of settles and go up, we kind of create a barrier. So that's kind of almost going to be a protected zone. So this is really favorable for, right, the coral growth. So hence why you get the Great Barrier Reef in Australia. So this is good land formation, relatively shallow, relatively safe, right? A lot of places too for the coral to make its deposits in and start growing and becoming all that is a reef. So of course a very diverse amount of organisms there. And so you could also happen where this mountain gets eroded in the center or goes away, and you are just left with this atoll here and your lagoon in the middle. And so that, again, is also still a really favorable environment. And so again, just showing how this might evolve. So going from the barrier reef and still having some land, and if your island sinks back, with a lagoon. And so you can see the evolution and how this has, again, changed and moved the Great Barrier Reef and all that land formation. And so this last little bit is just showing how we think the continents may have been over time. Oh, let's put a last minute note here on barrier reefs. And so, right, this is a great feature that can occur, but people recognize how awesome this is and have, of course, started even like sinking ships or other, right, oil rigs to try to create more land masses for corals to grow off of. So people really recognize how special this land formation is. And so we as people are like, how can we contribute and add to more spaces for organisms? And so, yeah, any sort of vessel can be, of course, a place for life to grow. All right, so yeah, last little bit of chapter 2 before we shift to chapter 3 is just these paleogeography. And so, right, paleo, ancient, geography, so obviously study of how those continents may have moved. And, you know, again, we'll never really know, but we can at least estimate. And the one thing you do want to be familiar with is obviously Pangea. That's very famous, just when everything was one big landmass. Question? Okay. And of course, right, they may even, I think the video that we watched, Colliding Continents, kind of went crazy at the end. It was like, maybe it might look like this in the year. I mean, who knows, right, what could happen. But we can kind of predict and model based off of what direction they're going. Cool. All right. Before we shift gears, let's practice what simple kind of math you might have about this chapter, not to give people anxiety, but to give you confidence about what you might see on your exam. And so let's say if the mid, and I don't actually have the rate, so I'll make one up, mid-Atlantic ridge is spreading at a rate of 2 centimeters per year, how much further will North America and Europe be in 50 million years? So just take a few minutes, think through it. It's not meant to be hard or tricky, just anybody have an answer or, yeah.
Could be wrong, but it seems super simple, like at 100 million centimeters.
Yeah, I think. So let's just type it out, and so if it's 100 million, I should have probably asked for it. So 100 million, so you would be correct. So 100 million centimeters, and maybe we should do a conversion. So convert to kilometers. So do you remember how to do that?
It's 100,000 centimeters of kilometer.
And so you could do so this would be a fine answer. If I wanted to be tricky, I could do a part 2, and so we could set up our conversion factor, and you could do it whatever way. So I'm doing centimeter, it's 10 to the negative 2. Kilometer is 1 times 10 to the 3rd, so some people were saying there's 1 times 10 to the 5th centimeters and 1 kilometer. And on this note, I am in the process of grading lab 1, so I'm trying to make sure to grade it for accuracy so you guys know what you're doing right, wrong. So I'm in the middle of that. I'm trying to grade as fast as I can, so appreciate your patience. So 100 times 1 times 10 to the 6th for 100 million centimeters. And so now we just have to do the conversion, kilometers on top. We're basically thinking of dividing by that. So just doing the division. And so what do we get for it? We could plug it into.
1,000 kilometers.
Yeah, so it should be 1,000, kilometers. Yeah,
I'm just going to offer for anyone who hasn't done fractional exponents, so you take 100 million and divide it by 100,000.
yeah, and you can always, so we could plug it in, so 100 times 10 to the 6 divided by 1 times 10 to the 5th. And so you get your 100,000. If the mental math, because you can do the subtraction or just punch it in is just fine. Questions about this? Yeah. And so that, again, might be the little simple math that I might put in there, because, again, that's what, right, the scientists are at least trying to estimate based upon the rate that we see, you know, assuming that it's somewhat constant, what can we kind of guesstimate? This is how they make those models, again, the best they can. Right. Any other last thoughts about chapter 2 before we try to get through chapter 3 today? Okay. We will keep marching forward then in summer term. Were you ready to move on? Sorry. Were you still looking at the map? Sorry, I should have asked. Just too excited with our summer pace. No. So today's lab is related to chapter 3. So you're basically going to be doing it kind of old school style. So how did they have to do it like really back in the day before we had any sort of sonar? Yeah, sorry?
I had a quick question.
Yeah.
But it was about the organisms of the week projects that we're going to be working on.
Oh, yeah.
Our first one will be due Thursday.
Yep. So,
Physical lines.
yeah, so physical lines. So you can imagine, right, how incredibly tedious was that? Plus, I mean, you're limited by your rope, so we didn't make it to the bottom, like, oops, you know, plus, so however long their rope was. And so that's kind of crazy to think about, like how inaccurate the map would be. And so you'll get a taste of that today in lab. You'll do your own little bathymetry with little sticks, kind of simulating that idea, and you'll try to draw it out your unknown floor and see kind of how well you do. And so it's really fascinating kind of how this has evolved. And so of course they started with echo sounding, so that was really the first evolution. And of course now we're up to satellites that give us much more detailed information, and I'm sure they're continually analyzing and trying to refine the data. And so again, like we were seeing in chapter 2, we know that of course these ocean features are generated by that plate tectonic activity, so we've kind of seen at least the evidence for that. And so you, of course, have different features exist in locations, and of course we see how all that kind of reinforces the continental plate theory. Of course. And so, like y'all mentioned, so of course the first soundings were made physically, and so that sounds like a terribly painful and tedious method, but it's what you had to do. And so this might be something that could come up as a conversion, so I could, you know, ask you something about convert fathoms to meters or feet. And it was just their length at the time. It was just like a length of rope. They called it a fathom. That was just their standard. And so, of course, today, now that's approximately 6 feet. And, of course, they had to measure, right, how many fathoms it was. And so kind of the first one to make systematic measurements was this HMS Challenger. And whose ship was this again? Or who piloted it? It was just trivia. It's okay, it's probably not relevant. Never mind, it's okay. So the Challenger, though, made systematic measurements, so it was dragging, a line behind it. And so later they switched to echo sounding, so that was started in the early 1900s. And so again, finding that the deep floor has variations. And so of course, it can only go so far sound, so there was still some issues, especially mapping the deep features. And so of course they noted here that sometimes if you got weird scattering, that might be some sort of organisms. So of course there was fuzzy data, but otherwise, you still can get a pretty good idea for these features, so that's kind of fascinating. And so of course, right, over time, just things get more and more precise. So then you have the precision depth recorder. So now you're, again, just using sound beams. So how long does it take the beam to come back up? You analyze that and then do mappings. And so just over time, right, these things get more complicated. So now the C-beam has multiple echoes, so then you can kind of analyze better the angle as well and how all those things come back and map it out. And of course, what's the limitation with all these, sounding methods? Even though this is nice, what's...
Because it'll pick up anything it bounces off of. So you're not gonna exactly see exactly what it is.
Yeah, so that's always a limitation. So really, right, you're only measuring, I'll say the bounce or reflection.
It's the distance from the step. So, it's coming from there, it's gonna hit here, and then the next one's immediately gonna go right here. So you're gonna know that there's a dip. You don't know if this is solid, you don't know if it's, you just know that there's something solid that it hit and bounced back. You don't know if it's 2 inches or 100 feet.
Right, yeah.
It could just be a table or it could be a rock. I mean, sonar's a funky thing.
Yeah. And so that's another limitation. So what are some other limitations of this? Think about, how does it have to get the measurement?
Say that again?
How does it have to get the measurement? Oh, sorry, I'm thinking more like broader. Like, how do you get the whole seafloor though? Like, what's the issue? Yeah, so you have to drive it, right? So that's still the problem, that even though, right, they're getting more and more advanced, you can tell, like, the different levels, maybe they can even tell, like, composition, right, with how the sound, with all that analysis, you still have to drive physically over it. So have to drive, I think they use the term, right, lawnmower, the lawnmower approach, right? Right, so I like that, point specific, right? So you have to literally check every point. It's just your resolution with the sonar can get better and better, but you're still mapping every point. So this is still obviously an extremely tedious way to map the ocean floor, and of course only a small percentage has been mapped by that. And so, right, again, it mentions the side scan sonar, so that's more detailed resolution, and how it even has a special instrument that can help get deeper right above the floor to again get a better detailed mapping, but you still have to physically drive over it.
And side scanning is actually really, so when I was tournament bass fishing, I had a sonar on my boat, and I had the side scan, and you can shoot it out about 100 feet both ways, and you'll see, like, it'll pick out, you'll see fish on there, you'll see grass, you'll see weeds, and it really does make a really cool picture.
Nice.
The sonar does.
Yeah, and then so did you see that data gap then too that they talk about?
Yeah,
where
you'll see
yeah.
Where your boat is.
Right.
You'll see like a gap in between, and I had down scan too, so on a different
cool.
screen you could see
Oh, nice, that's cool.
the center, but you were having to look at 3 or 4 different screens to really get a full picture of what was below you.
Yeah. And so, yeah, y'all can get a sense from that, just how much data too that has to be, and like trying to put it all together, like it's
constantly the whole time, or, something swims underneath you, or a log is going there, it'll mess up the entire picture, and then, so it's a funky thing, it's hard to teach somebody how to read that stuff.
Yeah, isn't it a lot of computers anyways, just like analyzing everything and then, well, then you still have to kind of
You still
interpret
have
the
to
picture.
dissect, so you'll see everything, like, so it'll just look like, thermal vision, you'll see you'll learn like what this shape is, it'll be like, it'll look like somebody took a paintbrush and just went like this, like just made some arches, you're like, oh, that's some kind of a weed down there. Or you'll see like something that's really cold in colors and solid and not moving, okay, that's a rock, or, something, it'll show like yellow, bright for like a sandy soft bottom, and like if it's hard, it'll be blue. So you just have to kind of learn what colors and
Yeah.
temperatures, it's, like I said, it's hard to teach and learn how to read that stuff.
Yeah, it's in the eighties, one of my best friends was a sonar technician in the Navy, he done an ROTC, done the whole thing. It was one of the most trained positions in the Navy. That was like, it's progressing computers and bits, but, like, they were like, you signed for 10 years, and he ended up, whittling himself out with a bunch of AWOLs and stuff, he just decided not to partway through, but, it was one of the most exhaustive training programs in the Navy, was sonar technician.
That's amazing. So hopefully that gives you all an appreciation of just like how amazing this data is, like how difficult it is to map with this, like it's all,
If you read it wrong too, it can be devastating.
yeah,
If you read it wrong, you're like, oh, I thought that was that, but it was a giant rock, and there's your boat.
yeah.
You got a giant hole in your hull.
Well, that's another
So
issue.
it does happen if people misread it, that's why it's so important to be able to read it correctly.
Yeah.
Because bad stuff, costly, fatal accidents happen because people read that stuff wrong.
His primary function was programming and firing nuclear-proof missiles, so it was something they wanted to be spot on about.
Yeah, because essentially those guys that use sonar, they're driving blind. They're just using the sonar to be like, okay, we can keep going straight, or
Yeah.
something coming, we need to.
Yeah, because I mean, you have to appreciate that, right? You can't see in the sea, like, and that's all, the other problem with trying to study the seas. We can't just look in there and even see anything. So, yeah, that's fascinating experience. And so, right, we see the limitations with sonar, and so now we have moved to satellites to give us a more accurate picture. And of course, we have to compare this to our sonar data as well, so it's good, right, to map these two. So what the satellites do is they look for little anomalies in the gravitational pull, so depending on the features. So basically, the features are so large that they can impact the wave structure itself. And so the satellites are super sensitive, and so that's also what's fascinating. I think I mentioned this with like the sea level, like trying to track how the sea level rises or doesn't rise, is that our old measurements were kind of made by hand, and now they're made by satellite, but they're super accurate now. So satellites are way more accurate, so like within a margin of error of like 4 centimeters. And so they look at this data, they look for any sort of gravitational anomalies, so that's what's graphed here. So either a negative gravitational anomaly, so showing something maybe deep is pulling it down, versus a positive gravitational anomaly where it's going to kind of create higher features, so seeing that. And so our deep ocean trenches are the darker color, and the lighter ones are shallower, green, orange. And so again, you would have to initially calibrate your satellites to see what the difference in kind of ocean level is compared to what the sonar says, kind of put that data together or put the mappings together to give you this picture. And so now this is really fascinating because it gives us a whole global view that we couldn't get with prior to obviously physically driving out and doing all that, which would not be feasible. So obviously we can't physically do that, so satellites give us a lot more, at least large picture, and it's still extremely accurate. So that's kind of what's fascinating is, the picture with the satellite is much more detailed. Where did that picture go? Thought I had a comparison somewhere. Oh, I'm not sure where it is. But also, you know, this reveals kind of new features, so you can see now again the global picture of where the trenches might be, where mountains could be, different formations. Again, you can see how that tracks along the different continental plates, and that could also tell you where do we need to go out physically and maybe map this in person, check it out, you know, on site, which again is incredibly difficult to do. So, you know, you can't just go down there and dive down super easily. I think we are becoming well aware of that. And so we won't worry about this map today, but basically all we're kind of saying is this is another way to figure out what all the different rock layers may be. So this may tell us, you know, how we can drill. And I'm sure there's a lot of money to be made being trained to do this well and analyze that. So I'm sure oil companies pay good money for geologists and other scientists and engineers to tell them that there could be oil here or there. Obviously, everything's still just a betting game and what we can guess, obviously based off of other successful profiles of whatever you're looking for. And so again, just comparing different detail with different methods. Let's see. All right, so let's look at kind of our different provinces. And so these are just definitions, really. So we have our continental margins of plates, and so this would be shallow water areas close to shore. And so you can see right where this is, so just all along the shoreline mapped out here. And so other features are, of course, our deep ocean basins. And so typically, they're going to be found farther from land. So if we go back up, not to drive y'all dizzy, right to this picture, we can see down over here, deep ridges, you know, deep ridges over here in Asia. So there's our ridges. And then, of course, we have our mid-ocean ridge. So kind of, they call it the submarine mountain range. So it's kind of in the middle. And so this is a good side profile. So again, your continental margin is a lot more shallow. And our deep ocean basin versus our ridges, especially where we're getting new land formation. So again, think our mid-Atlantic ridge. So new land. So mountain formation, or underwater, we should say. So those are just kind of our three general features. And so we can, of course, have passive versus active, and again, just a description, and like you might assume. So if it's passive, that's not close to any plate boundary, so no major tectonic activity, such as the east coast of the United States. And then anything active, right, that's going to be at the plate boundaries. So with your generally associated with convergent or transform, again, right, either making mountains, so continents coming together and crashing, or the transform plate boundary, again, like our San Andreas Fault that we're all familiar with in California, and that activity. And so looking at these different, again, regions, we're just kind of looking at our seafloor and how we can classify these different features. So we have our convergent active margin. So again, they're coming together. And so in our oceanic continental convergent plate boundaries, we would expect, of course, volcanoes. And then we might have a more narrow shelf as it's kind of coming together, so that means, right, our land is probably being compressed. Again, giving that narrow shelf. And so here's a good, so that's happening right over here. So we have an ocean trench. So this is a kind of a little depiction. So again, notice how small that little continental shelf is. So very narrow, and then it kind of trenches. So again, just kind of think about that, of your oceanic crust going in and meeting that continental crust there. And so a transformed continental margin, those are going to be, you could see those in the linear islands, so those would be good indications of some sort of transform movement, or maybe a deep basin close to shore could be unusual. And so we'll look at this as we continue. So we have, again, our continental shelf, and then notice how it starts dropping down in our continental slope, and then our continental rise here going to our abysmal plain. So again, just different features. Oh, and like we mentioned before, so of course we can have, right, seamounts, our little volcanoes. Just a little more detailed picture. And so another feature to familiarize yourself with is the shelf break. So where you have the drop off here, and again your continental shelf, right, all kind of flat out, coming out from our continent. And then notice right after your shelf break, there's your continental slope, and then your continental rise there. All right, so these are just words now to help with those pictures. So again, you have your flat zone and then your shelf break. Again, looking back at the picture. And so this is part of our continent, and the average width is somewhere from 70 to about 1,500 kilometers, and that goes back to, way back to what we were talking about, those first estimates in the 1960s, and why that, again, the estimate of about 1,000 kilometers ended up kind of working. So of course, now that we've mapped this out more precisely, we can go back and actually, you know, get a better picture, piecing those continents together, now that you have the actual width. So and so the type of continental margin determines the shelf features, and passive margins have wider shelves. And so you could look at all these different features that are just off of the coast. So this is just looking off the coast of California. So here's the San Andreas Fault. And so there's different, again, you can see how detailed this is. So there's troughs, so that's going to be lower, you know, wider basins, so a lot of basins, and of course you can see the features. And then of course closer to the continent, right, there's going to be your mainland shelf, so all along here. And so we have, right, our continental borderland. So this is where our deep ocean basins begin. And so again, just like we see on land, they have variable topography, just like mountain ranges, so very detailed features. And so then we have our canyons here. So we can have these submarine canyons, and of course that can create some currents. So these two turbidity currents move down slope, and that of course leads to the erosion then of the continental margin. And so then the continental rise is the transition between our continental crust and our oceanic crust. And so you can have some kind of graded bedding then from your turbide deposits and see that layered. And of course, this is a sample that they think was in the ocean and then came up. And so again, you can see that gradient bedding there. And so then, looking here, so we have canyons here, and some material can be deposited then in these canyons. And so these deposits then start making what's called these fans, deep sea fans or submarine fans. And so these deposits just kind of extend the base of the continental, and so they create kind of deep, flat parts. And you can appreciate that in this picture here, right? So notice this area here, which they've called the Indus fan, is just a really large area, relatively kind of in the middle, that's flat. And, you know, you can see why it's a fan, because it's large and flat, so it kind of makes sense. Large, flat, and deep. And then, of course, suspension settling. So you can see this just on your small local scales. You go to the beach, right, shake up your sand. Then, of course, things start to settle. And so suspension settling would be eventually, right, these fine particles come out. And so sediments, of course, cover the ocean crust everywhere. And lots of different features in the Atlantic and Indian Oceans. So let's look at. So again, just appreciate the detail on this as well. This is, and then we can see the abysmal plain, so located between a continental margin and mid-ocean ridge. Again, large flats, so you can appreciate that. And again, you may see volcanic peaks, so the point is, it can also be very varied what we see. We can have large areas of flatness, even deep in the earth, or all sorts of mountainous features. So we saw this kind of last chapter. Again, our seamount feature. So this is just kind of showing you how deep it could be, and again, depending on when it was made, how it was eroded, it could still be sticking out, or it could have your outliers creating that lagoon. Yeah.
And the Gulf of Mexico and the Mississippi be a good example of how the fans form.
Yeah, that would probably be a good example. Let's look. Yeah, because I'm just thinking, I would have to look up if anyone's actually like labeled it and defined it as such. I think that would be the next step. Was it in the last chapter? How come I can't find, where was that picture? There we go, this is what I'm looking for. Yeah. So we could zoom in, so we'd want a better picture, but it looks kind of wide and range there and kind of flat, so yeah. I'd want to follow up your question with like another map to look at that in detail. But, I mean, you have the right idea, is mapping those features, you know, how can we study them, label them, just kind of better understand what's going on at each individual part. And so this is just showing how deep our trenches are, so just re-emphasizing that. So like we said, these convergent margins, especially oceanic, create those trenches. They're in the deepest part of the ocean. And again, remember the Mariana Trench, we keep bringing that up, but it's just a very deep, prominent feature. And so here's just an average. So you can, again, just get a sense of how deep it is. And this is in kilometers, which may or may not be easier for people to grasp, but just, again, appreciate the range, you know, they go very deep. The deepest one are obviously in the Pacific, so remember that we kind of stated that from chapter 1. The Pacific is the biggest ocean, it has the deepest trenches, and then of course the Atlantic isn't too far behind. And like we mentioned, chapter 1, right, Indian and Atlantic are pretty similar in size, so it makes sense that the depths of their trenches would be relatively similar, with the Indian being a little smaller, which is what we said, right? Indian Ocean is just a little bit smaller than the Atlantic, so it all kind of fits in a pattern. And so again, just showing the trench lines here in purple, so you can look at all those trenches. Again, all of this helps to reinforce our continental crust theory. And so what you could also have happen with the oceanic crust is you can, again, have your volcanic art on your non-subducted ocean plate. So, of course, your subducted plate is essentially supplying the material, and then it comes out a little bit further down the line in your non-subducted plate. And so, again, we see that our islands in the ocean in Japan. And so you could also get mountains from this on the continent, so probably that's what led to the Andes Mountain. And so again, starting to at least get maybe a little repetitive, but at least you're seeing, right, all the actions happening at the boundaries, how they meet, dictates what activity we see, kind of what features. And again, we're just trying our best to piece together what might have happened with all this amount of data that we're trying to take in and understand. And, you know, the way I would look at it, there's plenty of area for research here if you're interested in it, if it tickles you. You know, you can always dive deeper into something. And again, check out your career, though, futures. And so we've kind of, again, said this. Feels a little repetitive, but just a recap. Your mid-ocean ridge here, so our longest mountain range, or the mid-Atlantic ridge, we should say. Mid-Atlantic, so we keep talking about this. Pretty important. So again, longest mountain chain, so very long. Obviously it's volcanic, so it's new. They're studying it. Basaltic lava, so that's just characteristic of mantle. And of course, again, divergent plate boundary. So we've said that. We saw this reinforced with our rock age. Yes, new stuff is coming out there. We can measure out the oldest stuff is on either side, newest stuff in the middle. So telling us it's divergent. So let's see. And so is there a picture of our Rift Valley somewhere, a better picture? Pillow lava. I guess we don't have a Rift Valley picture. So Rift Valley would just have a lot of fissures and faults. Again, just kind of what you might see on the surfacing of San Andreas Fault, but kind of in the ocean. And you're going to have small earthquakes. And so these pillow mounts, or pillow lava, so these are just kind of weird formations, and you can, of course, kind of see why they're called pillow lava, right? They're big, weird, shapy. And so that's just when that molten lava comes out, so it's hot, it's basaltic, so that's why it's black. And so it just cools really quickly, so it comes out as that weird big blob shape. And so, right, you could probably devote a whole semester into studying hydrothermal vents. So, you know, people have tried to exploit these for energy usage. Oh, I can't spell anything today. Energy, there we go. So could we potentially exploit this somehow? What's going on there? Like people are interested in the chemistry behind it. Like what's going on? There's also what organisms can tolerate this, what bacteria. So there's so much to study. And so, right, again, because they foster unusual deep sea ecosystems, because they're deep, they have no source of light, so their only source of energy is those hydrothermal vents.
So being that we have hot springs here in Ashland, are those created by hydrothermal vents?
It's like similar sort of idea, so there's some sort of like volcanic activity, so these hydrothermal vents, though, that's going to be like deep down, but same thing, right? It's just some sort of hot spot. Yeah, different scale, different location. So this is in the ocean, but the hot springs are like a mini scale on the continental crust. Like for some reason, there's some hot spot there in the hot springs, right? Again, we're not entirely sure what creates those little hot spots, but that's the idea. There's a hot spot there, and you know, probably some water formation, so that's keeping that hot. And so you have different classifications too. So you have warm water vents, which are obviously much milder conditions. And then white smokers are going to be hotter. So, you know, kind of mildly extreme, but still obviously, you know, 30 to 350 degrees Celsius. So that starts getting extreme, especially what organisms can tolerate that. And then black smokers is, of course, extremely hot. Temperatures above 350 degrees Celsius. And so again, these black smokers can also be giving out some sort of metal sulfides. And that just, again, depends what the exact composition is there. And so, right, any sulfide is just, like it could be iron sulfide, although there's probably various forms of iron sulfide. That's probably the most common one, is a lot of iron sulfides. Yeah, probably nickel sulfides. We mentioned our transform faults. So again, where they're kind of sliding. And so this just gives, okay, let's look at kind of the picture while we look at this chart real quick. So we look at, right, do we have a plate boundary? So if it's yes, then, right, that's our transform plate boundary. But if there's no, so it's just an intraplate feature, so it's not found right at the boundary, so not at the boundary. So in the plate, right, intra, like inside that plate, then you have then a fracture zone. So you could analyze that, right? Looking at your fracture zone, is it at my fault line? No, so then it has to be a fracture zone. And so, of course, y'all mentioned with the transform faults, that was opposite direction movement, right? We could measure that. And a fracture zone, though, is going to be movement in the same direction. And so, again, we're familiar with our San Andreas fault. We know that there's many earthquakes, relatively speaking, on that San Andreas fault, so there's lots of little ones all the time. And while a fracture zone, there would be few earthquakes. And so, of course, the transform fault on the plate boundary, this would occur between the offset mid-ocean segments, and this would be beyond it since it's in the middle. And so again, San Andreas fault, we can't say that enough, versus our fracture zone. You have these two fracture zones in the Mendocino and the Molokai fracture zone. So that is right on time and a good place to end. So yes, just a quick reminder. So your organism journal due. And as you're on your way out, I'll show, I'm sure you saw this, maybe Joe Rogan was like tweeting about this, so this was making the rounds on the internet. I'm going to try to remote in from my other account. So what you should always do is we should look at the real literature and see what they actually say. But this is kind of interesting, just with what we've been talking about, the age of the Earth. And so this is the age of the universe. And they just jumped from 14 billion years to now they're saying like 26.7 billion years. And so all that is from the redshift calculations. But I just wanted to put this out there for y'all to read, but then also put it out there for there's still tons of research to do, right? Because who knows if this is right either. So you can come along and analyze their data and maybe do your own research one day. So that's all I wanted to say. And so you always want to look at the journal articles. So anytime you look at a news source, try to look back at the primary source. And if you email me, I will be more than happy to try to give you that journal if I can get it through my old credentials. So, all right, we'll end there. So I'll see you in 10 minutes for lab.